This presentation is part 1 of Unit 3 of the subject Strength of Materials. Unit 3 covers the definition for elastic curve, the definition for slope and deflection, proof for the governing differential equation, and finding of slope and deflection for the determinate beams using different methods like double integration method, Macaulay's method, area moment method, and conjugate beam method. If you design any structure, it should be strong and stable. In addition, the structure should also be checked for its stiffness. When any structure is loaded, the deflection and deformation will occur, but it should be within the allowable limits. If the deflection exceeds the limit, the structure will fail. Therefore, any structure or structural component is designed, it is necessary to check for its deflection. So, what is deflection? We will discuss in the next slides. Before this, we should know what is elastic curve. When a beam is loaded, the beam will bend or deflect. Therefore, the configuration of the longitudinal axis of the beam changes to new shape like a curve. This deflected or curved shape is known as elastic curve. The elastic curve can be represented by an equation, right? Suppose if it is a beam, and it is loaded, it will deflect like this, right? This is the original profile of the beam. This is the deflected profile of the beam. After the loading, it will deflect like this, like a curve. This deflected curve is known as elastic curve, right? Elastic curve. This is known as the deflected shape, is nothing but elastic curve of the beam. After the load, the beam will deflect. The deflected profile is known as elastic curve, right? So the elastic curve can be represented by an equation. Here, actually, what is slope and deflection? The displacement of the neutral fiber from its original position at any section is called the deflection at that section. The deflection is generally denoted by the Greek letter delta. What is that? Delta. Yeah, this is known as delta, right? What is the deflection is denoted by the letter delta, and the unit for the deflection is mm. And what is slope? If you draw a tangent to the curve, elastic curve, the angle between the original profile of the beam to the tangent is known as slope of the beam. Slope is denoted by the letter theta. And what is the unit for this theta? That is radians. Okay, right. So here we have two diagrams. One is deflection profile of a cantilever beam. Another is deflection profile of a simply supported beam. Right? Right. So suppose if it is the beam, right? It is deflected, no? Right? If you deflected, no? The vertical displacement from the original profile of the beam to the deflected profile, this is known as deflection. This is known as deflection delta. if you draw a tangent, if you draw a tangent to this deflected shape, draw a tangent, the angle between the original profile of the beam to the tangent, this is known as theta. That is slope. Okay, it is original profile of the beam. If you are drawing a tangent to this deflected shape, the angle between the original profile to the tangent is known as theta, that is slope. If the tangent is drawn from the point A, that is theta A. Suppose if you draw a tangent to this end, that is at B, it is known as theta B, right? It is known as theta B. Similarly, the deflection is measured at C. Suppose if the point is C, if you measure the deflection here, the delta is C, right? So you can measure the deflection at any point of the beam, right? Okay. So here the first diagram shows the cantilever beam, the profile, deflection profile for a cantilever beam. This is the deflection. This is the deflection of the cantilever beam, that is at B, that is at free end, the beam will deflect like this. So it is delta B. But at A it is fixed end and there is no deflection, right? So what is theta B? You are drawing a tangent to the deflected profile. This is the tangent. It is the original profile, parallel to the original profile, a straight line. So the angle between this original profile of the beam to the tangent is known as theta, right? Similarly, for the simply supported beam, the deflected profile is known as elastic curve. This is tangent to the end A, so theta A, and this is the tangent to the end B, so theta B, right? The deflection at the point C, so it is delta C. Yes. Then what is pure bending? When a member is subjected to equal and opposite couples at its ends, the beam will bend, and the bending is said to be in pure bending. That is, at one end a clockwise moment is applied, at another end anti-clockwise moment is applied. Only the moment, and there is no axial force, and there is no shear force, and there is no torsional force, no other forces. Only the moment, that is couple, that is clockwise moment and anti-clockwise moment. These two moments was called, what is that? Couple. When we apply a couple, only the moment, not other forces. If we measure the bending moment, only applying the moment, that moment is called pure bending moment. Pure bending, right? So pure bending is a condition of stress where a bending moment is applied to a beam without the simultaneous presence of axial, shear or torsional forces. So bending of beam due to only the moment is called pure bending. Note here, bending of beam due to only the moment, no other forces, is called pure bending, right? Okay. Then what is this? It is bending equation. Actually, from the unit 2, you have already known well about this theory of simple bending, is it not? M by I is equal to F by Y is equal to E by R. This is known as bending equation, right? Here M is the moment, I is the moment of inertia, F is the stress, Y is the centroidal distance, E is the modulus of elasticity, R is the radius of the curvature, right? Then you know the deflected shape of beam is called elastic curve, right? Here the elastic curve can be represented by a differential equation and is known as governing differential equation. What is the governing differential equation? Any curve, it can be represented by an equation That equation, that differential equation is called governing differential equation. If the equation for the elastic curve is known, we can determine the amount of deflection, the angle of rotation, the bending moment, and the transverse force for any section of the beam. Right. Here actually EI into d squared y by dx squared is equal to m. This is the governing differential equation for a beam. Here m is the bending moment, you know well. Y is the deflection of the beam. And what is EI? EI is nothing but modulus of elasticity and moment of inertia. So the product of E and I is the flexural rigidity. Flexural rigidity can be defined as the resistance offered by a structure while undergoing bending. It is the product of E and I. E and I, the product of E and I is known as the flexural rigidity. This is known as governing differential equation. Right? Okay. So this slide, how the differential equation for a beam is arrived, right? See, actually, this is the differential equation for beam subjected to pure bending. Already you know what is pure bending, is it not? Right. Consider now we will arrive a differential equation for a beam subjected to pure bending, right? That is only the end moments are applied for the beam. Because of the moment, end moments, what is the bending? What is the bending equation? That is known as differential equation subjected to pure bending. Okay. Consider a beam AB subjected to pure bending, that is clockwise moment and anti-clockwise moment. Due to these moments, the beam will be bent into a circular arc and is known as elastic curve. Is it not? As the curve is part of the circle, right? Suppose if it is the curve, what is it? It is the part of the circle actually, is it not? For any curve, if you take any curve, the curve is a part of the circle. So the radius of the curvature is given by the equation, the radius. So any circle, it will have center. So from the center, it has some radius. So the radius of the curvature can be given by the equation m by I is equal to E by R. So m by I is equal to E by R. Already you know the bending equation, is it not? From this we can write m by I is equal to E by R. So this can be modified as 1 by R is equal to m by EI. So E come to this side, and so that we can write it as 1 by R is equal to m by EI. This is equation number 1, right? Now you know this elastic curve of a beam AB, right? Here we consider the 2 points P and Q for the very small length, right? In the curve we consider a very small length ds, right? A very small length of PQ. Let the angle of the small length curve be d theta, right? Actually the enlarged view of the small curve is shown in this figure, right? Yeah, this curve is shows a enlarged view of this small curve PQ, right? This PQ of length ds, let it be ds. Its subtending angle d theta, right? So the radius is r. Okay, so since the curve ds is very small and may be considered as straight line, right? The points PQ are projected, right? Suppose if it is a curve and it can be projected from here and from here, so it forms a right angle triangle. So it is a small length, the curve may be considered as a straight line, right? So it forms a right angle triangle PQS. We say the right angle triangle as PQS. It is shown here, right? Okay. From the figure, what is that? dy is the opposite side and dx is the adjacent side. So opposite side by adjacent side is tan theta, right? Since theta is very small, because it is a very small length, So theta is also very small. So tan theta may be considered as theta, right? Therefore, this expression tan theta equal to dy by dx can be write it as theta is equal to dy by dx. Instead of tan theta, we can write as theta. That is theta is equal to dy by dx. This is equation number 2. If we differentiate this expression, we will have dy by dx. If we differentiate this one, d squared by dx squared. If we differentiate with respect to x, this theta will get d theta by dx. So this will be equation 3, right? Now from the angle OPQ, right? The angle OPQ, this one OPQ, right? Listen again. OPQ, right? OPQ, right? Yeah, this is R, no? And this is d theta, is it not? So this ds, this is the length of curve ds. This ds can be written as r d theta, okay? Since PQ is very small, ds can be write it as dx. We know that, is it not? It is ds and this is the straight line is dx, is it not? So we can write the ds as dx because it is very small. ds is equal to dx. Therefore, dx is equal to r d theta. Instead of ds, we write it as dx, right? So dx is equal to r d theta. And from this, what we can write? D theta come this side. So d theta by dx is equal to 1 by r, right? This is equation number 4. Now equating this equation 4 to 3 because it is in the form of d theta by dx. The equation 3 also in the form of d theta by dx, that is d squared by dx squared, right? Equating equations 3 and 4, we will get d squared y by dx squared is equal to 1 by r. And from equation 1, where is equation number 1? This one, that is 1 by r is equal to m by ei. Putting this value for 1 by r, we will get, what is that? D squared by dx squared is equal to m by ei. From this, we can write it as m is equal to ei into d squared y by dx squared. The above equation is termed as governing differential equation of elastic curve for a beam. Okay, right. Then how to find the slope and deflection? On integrating the above differential equation, we arrived at the differential equation, is it not? M is equal to E into d squared by dx squared. If we integrate this one time, we will get slope, that is dy by dx. Again we integrate, we will get deflection, that is on integrating once, we will get slope. On integrating twice, we will get deflection y, right? Okay, then already we discussed what are the methods to find the slope and deflection. Actually there are 4 methods, right? We will discuss the problems for finding slope and deflection in the next part of unit 3. Thank you.